Hi, thanks for joining me. Today I'm going to be presenting my project on using additive manufacturing for flying wing aircrafts. Let's just start off with the applications and purposes for these aircraft. Because, of course, if an aircraft doesn't have any applications and purposes, then there's no point in making it, even if they're really cool. So, uh, Aircraft, or essentially air travel, is right now the fastest and safest method of travel. But it has one major downside, and that is cost. Right now, air travel is currently the most expensive method of travel. So, in order to solve that, flying wing aircrafts can greatly reduce fuel consumptions by making aircrafts more aerodynamically efficient. So that is probably the top application for this aircraft. However, there's many others. One being for smaller civilian aircrafts. Right now, they only have a few hundred nautical miles of range. So, essentially, like a Cessna, rather than having 500 nautical miles of range, it could be increased to like something like 800 nautical miles of range because flying wing aircrafts are more use less fuel, so they're more aerodynamically efficient, as I talked about earlier, and that allows you to fly farther. But it also increases the internal volume in an aircraft too, so it can also carry more fuel, and that will also further increase the range as well. This is also important for improving the flight endurance of drones. So right now, drones are very good tools for gathering data, using whether that be for surveillance, or essentially mapping out areas. So, for example, if you want to map out the Amazon rainforest and see how the environment change and look for changes in the environment, that would be a very good tool. And of course, having one drone essentially with higher flight endurance would improve those capabilities. So, because it would allow you, of course, fly longer. And then third, the final application essentially is for alternatives to internal combustion engines. So right now, electric and hydrogen propulsion has been discussed a lot for use in aircrafts, since they have no direct emissions, unlike fossil fuels, and they also, more importantly, also potentially reduce the operating costs of aircraft, especially electric propulsion. And right now, the big problem with those two methods of propulsion is that they can't fly as farther. Lithium ion batteries right now have a lower energy density, of course, than fossil fuels. And hydrogen, even though it has a higher energy density than any fossil fuel, since it's the lightest element on the periodic table, it has a very low density. It has a lower density relative to its energy density than fossil fuels. So hence, hydrogen-powered aircrafts can't fly as far as fossil fuel-powered aircrafts. But of course, flying wing aircrafts, by increasing their internal volume, or essentially its useful volume, and improving the range of the aircrafts by making them more aerodynamically efficient, could solve some of those issues and make these two methods of propulsion more viable. So, aerospace engineering is sort of like a balancing act between various different design domains that's grounded by the laws of physics. So, since the goal of this project was to make an aircraft that's essentially, or no, a flying wing aircraft that's aerodynamically efficient, make it using locally available 3D printers, and then third, make it, of course, stable enough to fly properly. So, since those are the uh, goal of the aircraft, the main design domains that are prioritized for this aircraft would be, of course, the manufacturing, because of course it needs to be made using additive manufacturing technologies that's done with locally available 3D printers, as I discussed earlier. And then, of course, it also needs to be aerodynamically efficient. It needs to be, of course, a flying wing. That's the whole point. So it needs a higher lift to drag ratio than a conventional aircraft design. And then third, it needs to be, we need to prioritize essentially the controls and the flight stability of the aircraft. It's the third design domain that's prioritized. But of course, there's also other design domains that need to take into account. So particularly the weight. It needs to be light enough to, of course, take off the ground. And then it also needs to be have a strong enough structure, so that way it doesn't fall apart when it's flying in the air. Because of course, having a plane that falls apart is not good. And then importantly, it also needs to have enough internal volume to house all the electronics, and of course, it needs a method of propulsion. So, because of course, if it doesn't have a propulsion system, then it cannot maintain flight. So that's all the design domains that were taken into account in this aircraft. So now I'm going to go over the problems with flying wing aircraft. So one of the issues with flying wing aircrafts is flight stability. So flying wings have been around for a long time. Jack Northrop was the first to make them in the 1930s. And one of the huge issues was the flight stability of these aircrafts. They were difficult to control. They would sometimes even essentially spin out of control sometimes. Of course, they didn't crash though, thankfully, but they were an issue, and that's why the U.S. Air Force actually didn't use them in the 1940s, because they couldn't control them stably enough to be actually use them in any practical area or application. So to solve that, essentially a lot of aircrafts use essentially a reflex airfoil, which unlike a laminar flow airfoil, it reflects the air backwards. So what that does is it makes it more stable across the pitch axis of the aircraft. And it also has a huge drawback, is that it makes the aircraft less aerodynamically efficient because it's reflecting air backwards, pushing less air downwards. And since airfoils work off of the change of momentum of the airflow, and that has two benefits. One, it decreased the static pressure, essentially the amount of potential energy in a fluid, and air, by the way, is a fluid. Anything that flows is a fluid. And that decreases, so it decreases the static pressure of the air above the aircraft, but the static pressure below the aircraft, since it's moving slower, is higher. So there's more pressure above the aircraft, or sorry, below the aircraft than above the aircraft. So that allows it to produce lift. And of course, that's what's known as Bernoulli's principle. It also produces lift off of Newton's second law of motion, which is force equals the change of momentum, or mass times acceleration. Because since it's accelerating air downwards, it's able to produce an upward lift off of Newton's second law of motion, as well as Bernoulli's principle. So of course, if you're reflecting air, you're not be able to produce lift as efficiently, and that decreases the lift to drag ratio. And essentially, aircrafts that rely on reflex airfoils, in a lot of cases, the flying wing ones, are less aerodynamically efficient than conventional aircrafts that use laminar flow airfoils. So that's problem number one. Problem number two that I identified in this project was, of course, that aircrafts, essentially the ones that use tubular design, are much geometrically simpler than the flying wing aircrafts that are based entirely off of airfoils. And that becomes an issue if you want to scale or down or scale up aircrafts. And so if you want to fulfill different passenger domains, you want to do that. So that becomes an issue with flying wing aircrafts. Because they're more geometrically complex, it's harder to make changes in the different sizes and make them more customizable for the changes in demands for different passengers, or different amounts of passengers. So additive manufacturing could solve this, but since it doesn't rely on any type of molding, it can essentially print out materials from the ground up, rather than essentially having to mold off of a certain mold. It has to mold the material off. So that's two of the issues with flying wing aircraft. So going into the aerodynamics of the fuselage, so these flying wing aircrafts could offer about a 20% increase in lift to drag ratio. But of course, one of the issues with these aircrafts is, as I discussed earlier, that they rely too much on reflex airfoils. So in this project, how I addressed this is I used the loft feature in SolidWorks to loft a reflexed airfoil to a more laminar flow airfoil that's slightly asymmetric, essentially. And by lofting them together, you get less reliance on a reflexed airfoil. And as you notice in the flow simulation, the air becomes less turbulent as you go from, and more essentially more laminar as you go from the center reflexed airfoil to the outer laminar flow airfoils in the fuselage design. And then, of course, to make up for the decreased reliance on reflexed airfoils, we use essentially a V-tail in the back that increases the pitch stability and also increases the roll stability of the aircraft. And it only adds a minimum amount of parasitic drag, and that allows us to greatly improve our lift to drag ratio of the aircraft. So now going into wings. So for the wing, I use an NCAA, or essentially a NACA 2412 airfoil. It's slightly asymmetric, and the reason why I want it to just be slightly asymmetric is that we want to have it be as aerodynamic as possible. But we want a little bit of higher coefficient of lift, so that's why I didn't go for a completely symmetric airfoil, so that way the stall speed isn't too low. And the reason why you want that is not only does it make it more aerodynamic, but it also means that it's more stable across the pitch axis of the aircraft because it's pushing less airflow downwards relative to the bottom airflow of the airfoil, and that makes it more stable across the pitch axis of the aircraft. So one thing you will notice about this aircraft design and the wings that it has is that they're swept back 35 degrees. And one of the common misconceptions about swept back wings is that they decrease the coefficient of drag of an aircraft. They do not decrease the coefficient the coefficient of drag of an aircraft at all. What they do is they increase the critical Mach number of an aircraft. And the critical Mach number of an aircraft is essentially the Mach number at which it enters transonic drag. So a typical aircraft that uses a straight wing will enter transonic drag at Mach 0.7. But by sweeping back the wings, you can increase that critical Mach number. The 0.8, in our case, it's 35 degrees, so it's increases from Mach 0.7 to Mach 0.855. And of course, the aircraft that I built does not fly at Mach 0.7 or Mach 0.855. Here it is. Is that right here? If you can see it. Hopefully you can see it. And so, place it back there. So, what this does is, as I talked about earlier, is that's one of the advantages is it increases the critical Mach number. This aircraft is not going to fly at Mach 0.85, if you didn't already know. And so, but however, it has two advantages to it for this particular aircraft, since it's not aerodynamically beneficial, but it is beneficial from a control standpoint, as I talked about earlier in the presentation about design domains. The control stability was one of the biggest design domains of this aircraft, and by sweeping it back, it actually improves upon the control and stability of the aircraft, because it gives more leverage to the ailerons, or in this case, they're technically elevons, since they also act as an elevator for the aircraft. And of course, that increases by sweeping them back. You're making it farther from the center of gravity, and that's what gives the ailerons, or in this case, we call it elevons, more leverage to the aircraft. It also benefits it from a manufacturing standpoint, because by having the wings swept back, you can essentially print more area for the wing in a smaller print bed, because it's going across the X and the Y axis, and you can maintain a high aspect ratio while increasing the surface area of your wing in a single 3D print. So those are the benefits. Going into the aspect ratio on this aircraft, for the wing itself it's 7, but the total aspect ratio of the entire aircraft is 8.35. So just for reference, the Boeing 747-400 has an aspect ratio of about 8. And that's very impressive for an aircraft like this that's a flying wing, because the aspect ratio is equal to the wingspan squared divided by the area. So for flying wing aircraft, since the entire surface area of the aircraft is included, since it's all acting as a wing, its area and the calculation for the aspect ratio is going to be a lot higher than a conventional aircraft. So it's harder to achieve a higher aspect ratio. So 8.35 is actually really good for flying wing aircrafts. And you want a higher aspect ratio to decrease your induced drag coefficient. Or essentially, induced drag is the drag that involves essentially the higher pressure air below the aircraft moving around the wing and interacting with the lower pressure air above the wing, or lower static pressure air. And the reason why it does that is, of course, because a lower pressure fluid wants to go where there's less pressure, and since there's less pressure above the aircraft, it will try to move around the wings. And of course, if your wings are longer relative to the area, it's harder for the airflow to go around the wing, and you can therefore reduce your induced drag coefficient by increasing the aspect ratio. So that's the wings for this aircraft. It's also important to know they also use blended winglets to also further reduce the induced drag coefficient, and they also reduce the Dutch roll, essentially prevent that, which is the spanwise flow that flows around the wing. Since they're swept back wings, there's spanwise flow that flows around the wing and over it, and that can cause instability across the roll axis of the aircraft. Blended winglets also prevent Dutch roll from happening, therefore, because it cuts off those vortexes that form around the wings. So here's the wing design iterations. As you see, there's a V1, V2, and V3, and I'll get into all of those in the next slide. Starting off with wing V1. So wing V1, I'm not going to sugarcoat it. It was probably by far the worst design for this aircraft, but it was also my first time designing a wing for SolidWorks. And it very poorly fits the design parameters of this project. For one, it uses a very highly asymmetric airfoil, and what that means is that yes, that makes it very well optimized for low stall speeds, but it has many disadvantages. For one, it decreases stability across the pitch axis of the aircraft because it's pushing more airflow downwards relative to the airflow below the wings. So it's not good for flight stability. And then the second big disadvantage that it has is that it greatly increased the induced drag coefficient, since it increases to the square of your coefficient of lift. So by using these higher coefficient of lift airfoils, they actually make it less efficient from a drag standpoint. So if you want a higher speed aircraft, you want your airfoils to be less asymmetric to make the aircraft more aerodynamically efficient. Another huge disadvantage with this aircraft design is that it has 4 times the wetted area. So that means it greatly increases the parasitic drag. And parasitic drag is essentially the typical drag that you think of in an aircraft. Essentially the drag that has to move around an object. So it greatly increases the parasitic drag by having more than 4 times the wetted area of the final wing design. And importantly, it also doubles the weight of the wings. So you have a lot more weight to the aircraft, and of course means that it needs a lot more energy to maintain flight and take off, which is a big disadvantage. It also used 2 wing fences for the design. So these wing fences essentially straighten out the span-wise flows I was talking about earlier. So they're good for flight stability, particularly across the roll axis of the aircraft. But I found out with using flow simulation and SolidWorks that these were not needed. And essentially, with the most notable aircraft that used the wing fences was the MiG-15. And these wing fences, what they do, they're not needed because they also increase the parasitic drag. They also add a little extra manufacturing time for the 3D print. And they particularly add drag in a particular type of drag called a differential drag, which is a type of parasitic drag, in which an aircraft essentially the drag between different surfaces of an aircraft. And since that also increases the drag a bit, so these were not needed, and it slightly decreased the drag. And then the next thing about this design that was not desirable is I used a 90-degree angle winglet instead of a blended winglet. This also greatly increases the differential drag in an aircraft, because rather than having a winglet that slowly converges out of the wing, it has a winglet that comes directly out of the wing, and that, of course, leads to more airflow between different aerodynamic surfaces. So that's wing V1. Now let's go to V2 and V3. I included them on the same slide because aerodynamically they're the same. The key differences relies in the structure of the aircraft, or the wings. And for V2 and V3, they both use the NACA 2412 airfoils, as I talked about in my first slide regarding the wings. The difference is in the use of carbon fiber spars for structural support. So Wing V2 is designed on relying on carbon fiber spars for structural support. It has great strength to weight ratio, but it has 2 disadvantages that left me decide not to use them. And the first one is that it takes up a lot of internal volume that's needed for electronics. And the second disadvantage is that it adds more complexity to the manufacturing process, since there's extra parts that are needed to be placed into the aircraft. So that left me using Wing V3, which uses a structure that does not rely on carbon fiber spars. And technically there's a V4, but it's a very slight change. Essentially, the first Wing V3 that I printed out, one of the issues was that it printed out horizontally on the 3D printer, and it created structural supports between the hole that's used for the axle that links the aileron to the actuator of the aircraft. And so, in order to make that hole available for the axle to go through, you would have to drill through most of the wing. And that is simply just not practical. So it doesn't meet the manufacturing constraints, since it's very difficult to nearly impossible to drill a hole that small through that far of a distance. There's too many imperfections, and it also ends up actually heating up the plastic and ends up collapsing in on itself, so it's practically not doable for this wing. So what I did, I put a channel through the wings with V4, and what that did was it created more area for the axle to go through. And essentially what I did was I put a straw in the channel that goes to the wing, and then I molded plastic weld around it to keep it holding up structurally, and then I put the axle through the straw of that's inside the wing, and that allowed it to move around freely and connect to the aileron. So that's what I finally used. So going into the structure of the fuselage. So for the structure of the fuselage, it's made out of a impact-resistant PLA plastic, and I decided to use a PLA plastic for this since it's fairly lightweight and easy to use. For the wings, I use PEGI, which it has much greater tensile strength, but it is a little bit more denser and thus heavier, about 11% more. PLA has 1.24 grams per cubic meter of density. PEGI has about 1.38 grams per cubic centimeter of density, so it's a little bit more denser than PLA, and that's why I did not use it for the fuselage, and that allowed my fuselage to be a bit lighter. And the structural strength isn't as important on the fuselage as it is on the wings, since the wings are longer and thinner. There's more stress on the wings, so that's why I went with a slightly heavier material that's stronger. So for the fuselage, one of the issues that I had with it was having a top that could easily be taken off and on, since I needed to place electronics inside there and potentially replace them or program them by directly wiring in directly wiring the essentially the electronics into my computer to reprogram them if there's ever a software issue. So in order to allow it to the top of the lid of the aircraft to detach and attach on quickly while maintaining good structural strength, I decided to create screw holes in SolidWorks. I did that using the Hole Wizard feature, and I placed 4 of them. And there, I can just put in screws, and the top is of course screwed in, and that allows you to take it off, put it on with no problem. So the bottom of the fuselage, it was originally designed to be printed in one piece, but since my larger 3D printer at the time was having issues, I decided to use a smaller 3D printer, and therefore I had to split it up into 3 parts. And therefore, it had to be super glued and also use plastic weld to connect all 3 pieces and make it have good structural strength, since those are good, fairly good epoxies that are good for connecting different pieces of plastic together. And then, of course, it has screw holes for a motor in the back. The servos were originally intended to be epoxied in, but I later found out that they were so good at fitting in, they almost fit practically like a glove, that I could just place them in directly, and they're so tight that they didn't need any epoxy. And then for the battery, I had zip tie holes, essentially are mounting points. That's used for the battery and the ESC, which controls the amount of power that goes to the electric motor. And yeah, that's the structure of the fuselage. So going to propulsion, originally this project was intended to use a electric ducted fan. Since it offers greater energy efficiency, since it cuts off the vortexes that are formed around the tips of propellers, the duct. Not only that, but it also compresses the airflow, so it makes it's a much more energy efficient method of propulsion than propellers. But they have major downsides. The duct greatly decreases the mass efficiency and the volume efficiency of the propulsion system. And what that means is that, one, you have to place it outside the aircraft. There's not enough internal volume to fit the ducted fan inside the aircraft for this particular design. So you have to fit it outside. And of course, it's a lot heavier than a propeller. And not only is it heavier, but it also requires a lot of outside structural supports, which add drag, as well as the duct itself also adds more parasitic drag. And then it also, since it's placed above the center of gravity of the aircraft, it has to be angled downward slightly by a few degrees. And that, of course, decreases the efficiency of the propulsion system as well. So ultimately, all these disadvantages led me to using a propeller, since it could be just mounted directly into the aircraft and did not take up all this space or add a outside structure that added extra drag. So that greatly was a much better option, even though it had lower energy efficiency. So going into the propeller that I used, one to essentially decrease the efficiency advantage between the ducted fan and the propeller, I used a new type of propeller that was developed called a toroidal propeller. So a toroidal propeller was recently developed by MIT scientists, particularly Thomas Sebastian was the one who came up with the toroidal propeller. And by having the propeller angle inwards and have a curved tip, it reduces the tip vortices. It makes it harder for essentially the lower pressure and the higher pressure vortexes from mixing together, and that reduces the amount of drag that's formed around the propeller, and that improves the efficiency. I went with a two-blade toroidal propeller, and I made it using my 3D printer. And the two-blade propeller has less pressure pulses per rotation than a equivalent three-bladed toroidal propeller, and so that makes it the two-blade more efficient. However, it does make it louder because the pulses of pressure that are produced by two-blade propeller are louder than the pressure pulses produced by a three-blade propeller. So that's why I went with a two-blade, because it's more efficient. So going to landing gears, the landing gears were a little tricky. Finding the right ones for this project was tough because Amazon on Amazon and most other shopping areas on the internet, none of these suppliers like to give the exact dimensions for the landing gears that are needed. And even for most of the ones that did, the landing gears turned out to be way too big for this aircraft. So I later went to my basement and found my old Cessna model plane that I used to fly around and crash when I was younger. And so I essentially took the landing gear out from that, and I found that it had a great lock-in mechanism which is used for mounting the landing gear to the aircraft. And it used essentially a small slit, and what you would do is you would compress the landing gears and squeeze it into that slit, and it would expand outwards and lock in to the mounting, so no epoxy or plastic weld is needed. And so I used that mechanism and implemented it into my CAD model, and that made it a lot easier to implement the landing gear inside the structure of the fuselage. So that made it a lot easier on the design aspect. So going into the front landing gear, I used a mounting point and then epoxied it in. In that landing gear, I found a line, and that one actually gave me the dimensions, and they were good dimensions. And the landing gear that I used for that offers great suspension capabilities because it has a spring on it and it's made out of aluminum. So I also used the mounting pivoting point to not only is it just a mounting point, but it's actually used to level the front landing gear with the back landing gears, the rear ones. And that's important since this is a pusher propeller aircraft. And what that means is that you need the front landing gears to be leveled with the rear landing gears, since the propeller's in the back and you don't want it to, of course, scrape against the ground. So going to electronics, so I used a 1500 milliamp hour battery, and that I placed in the front since the aircraft was actually a little tail heavy, and that helped balance it out, the aircraft, from a weight standpoint. And then I used an F411 flight controller, and that's like the brains of the aircraft. And what it does is it has essentially a lot of sensors inside of it. It uses a gyroscope, and it's a very small one that's linked to a couple of stators, and based off of the pivoting of the aircraft, and the gyroscope will maintain its orientation. And based off of the inner electrical charge that's being picked up from the stators, the aircraft can determine its position, or sorry, its orientation. And then it uses an accelerometer, which works off of MEMS technology, and essentially the piezoelectric effect, which is essentially a material that when you put pressure on it generates an electric charge. So it has a ball that's surrounded by piezoelectric material, and when the aircraft moves or accelerates, the ball will move around from that as a result of that change in acceleration and push against the piezoelectric material, generating an electric charge. So that's how it measures the acceleration. And it also uses the iNav software to provide active stabilization to the aircraft, and also flight plans, where essentially you can follow a bunch of points across a map. And so that's the F411 flight controller. And I chose it also because it was very lightweight. It's only 7 grams. It doesn't take up much volume. So that was another attractive option of this flight controller. So it also uses a 2200 kilovolt electric motor with a 30 amp ESC, and as I discussed earlier, that controls the amount of power that goes into the electric motor. And then of course it also uses 2 servo motors, or are basically actuators for the aircraft to actuate the 2 ailerons to control the aircraft. And those are all the electronics that were used. Oh, it also used a global positioning system with the F411 flight controller as well, and that's used, of course, to find its position, and it actually links to all 4 different international satellite constellations. So it works with the American GPS one, it works with the European Galileo constellation, works with the Russian GLONASS system, and it works with the as well as also the Chinese global positioning system as well. So that allows it to work more accurately if it works with all the different satellite constellations rather than just one particular one. So going to cost, some components were of course more expensive than others. The most expensive, of course, was being the flight controller, since it involved a lot of computing technology, and it cost about $60. And total, the aircraft cost $198.84, which is just within my budget of $200. So I just was able to fit this in within my budget before becoming too expensive. So yeah, that's my aircraft project, and thank you for listening, and I hope you have a great day.